Okay, so welcome everybody to the last module where we'll be discussing uh, initially Turing patterns. But today we'll have a more hands-on discussion how to discuss these patterns and why they're getting them. Various patterns. When are we getting stable solutions? What are stable solutions? When you solve all the points in the lattice basically reach one fixed point, right? So there are no heterogeneity in the density of A and B in the lattice. And just to remind you, we are solving Fithugh Nagumo equations, which are reaction diffusion equations, and broad perspective from the computational physics perspective is we are learning to solution of time dependent PDEs. Yeah. So Turing pattern comes from different directions. Reaction diffusion equations come from different directions. And Fithugh Nagumo, as I read up yesterday, uh, these two variables are also used to model neuron firing, where A and B are concentration of A sodium ions and potassium ions, and there's a huge background to it. But we are not going to get into it. But if you're interested, please read up. I got interested and I started reading up for my own interest, but not for the class. I can't be loading you with all the details. So where we left off in the last class, where for unstable solutions, basically if there's a slight perturbation uh, at any one point, then there would be a runoff, there will be a variation um, in the values of A and B uh, over space and time. And for the conditions for that is basically a set of these conditions, right? So you have seen it in the last recording. If not, please remind yourself. So these is derivative of the first of the R1A is with derivative of the first term with respect to A. This is the derivative of the second term with respect to B. And as a consequence, these two must have different uh, signs. So if one is positive, the other is negative. And for the Fithugh-Nagumo form that we have taken, uh, B is the negative term. Okay, so I'll tell it in detail. Moreover, we know uh, that these two terms have to be, these are the off diagonal terms essentially, they have to be of opposite sign again. And not only that, uh, basically, so they have to be opposite signs. So when you take a product, they are negative, and with this negative sign, there this entire term becomes positive, and that has to be greater than this value, right? So the product of this and this. Moreover, for this condition to be greater than zero, and since we know in our case R2B is negative, we know that the diffusion constant of B has to be greater than the diffusion constant of E, right? So these were the conditions which we had derived uh, from. So this is yeah, from the last class. Just to remind you, just to put it in perspective, these were the, so R1 was this term, R2 was this term, A is assumed to be between 0 and 1, and A is called the activator species. Why? Because if A is assumed to be between 0 and 1, basically if you increase A, del A, del T increases, right? So basically increase in A leads to a increase of del A, del T till it reaches some fixed point, suppose. On the other hand, increase of B leads to lowering of del A, del T. So in that sense, it's the inhibitor. And B is inhibitor for both equations. So here also it appears with the sign minus B, of course, product of beta minus B. And here also it comes with a negative sign. So that increase in B is going to decrease both del A del T and del B del T. So rate of change um, of del A del T and del B del T is going to be negative. So it's going to decrease the values of A and B. It's the inhibitor. And A does exactly the opposite. It increases del A, has a tendency to increase del A del T. Of course, there's a cube term also, so it does not allow it to fly off. I'm recording. Uh, and Basically, so this leads to suppression in quantities of A and B, increase in the value of B, and the rate of increase of B can be controlled by this beta. So if you have high beta, del B del T will increase at a fast rate, and if beta is small, it will decrease at a slower rate, right? uh, Furthermore, just to check, so I'm taking, so if we choose dA equal to 1, dB equal to 100, uh, alpha equal to plus or minus 0.005, and beta equal to 10, this choice of parameters, then we can see that if A is less between 0 and 1, then R1A, if A is actually quite small, it's smaller than, uh, yeah, because this has to be positive, then this is negative, which was the criteria, the first condition, essentially, right? R1A and R2B have to be, first of all, of opposite signs. So uh, R2B is this, right? So these two have to be of opposite signs. D is the inhibitor. Moreover, uh, I think R2A and R1B were supposed to be of opposite signs. That is also the criteria, which is basically R1B and R2A. R1B and R2A, they have to be of opposite signs. And diffusion constant of B has to be much larger than diffusion constant of E, right? So we essentially want, uh, with this choice of parameters, we satisfy all the conditions. But of course, we have to, we'll see when go away from these values of parameters, how does it look like. The other condition, just to remind you, you have must be careful of is, if you remember, the condition for stability the condition for stability of solutions was that this quantity must be positive for the explicit method, and that basically led to delta t must be delta x by 4d. Now for the equation for a, d is equal to 1, and we are going to choose, we're going to take a lattice 60 by 60, let's say. You can take also 100 by 100, but 60 by 60 if we take, and delta x equal to 1, and if d equal to 1, uh, then 1 by 4d, then t, we can even work with t equal to 0.1, say. But remember, db is, we have taken value to be 100. So then 4 into 100, 400. So then delta t must be smaller than by 4 by 1 upon 1 by 400, right? That means we can choose delta t to be uh, 1 by 500, which is 0.002, but we cannot exceed that. So we have to be careful. And while playing with parameters, we can easily decrease dB for the same value of delta t, but we have to be careful that if we go above, so we choose even higher values of dB, then we have to simultaneously adjust the value of delta t. So these are some things that we have to be careful about while playing around with the equations. With that caveat, let me basically, so this is the code where over and above the diffusion equations, R1 and R2 are also defined and implemented. And here I have just chosen uh, diff A to be 1, as I have diff B to be 100, diffusion constant of A and B to be 1 and 100, alpha you can choose 0.005, beta is been chosen to be 10. Right, these are the Fithugh Nagumo parameters. Somewhere I have defined the lattice size to be 60. Well, this is where I've defined the lattice size to be 60, Lx equal to 60 and Ly equal to 60. And the initialization of, there are these two variables, uh, and I'm using some random number between 0 and 1 to define these lattice. So temp A is basically, yeah, the density of A and density of B, if you like, right? And using old temp A, we are going to find out the new values of temp A at later times. And I have shifted old temp A minus 0.5. So the different values in the lattice, on the lattice, the different at different lattice sites, you have the random value of old tempe between minus 0.5 and plus 0.5, and similarly this. And what I'm doing is I'm going to run the iteration for 40,000 iterations. DT I've chosen to be 0.002, being in the careful about the choice of dt, especially since we are using the explicit method. Dx and dy is chosen to be 1. uh, the thing which I'm going to do is after every 1000 iterations, I am going to save a snapshot of A and B so that I can see what is the time evolution of A and B with time. And of course, there will be 40 snapshots because total number of iterations is 40,000, and I'm saving a snapshot every 1000 iteration. And this, of course, corresponds in terms of time, number of iterations into 0.002, right? So every time step of 2 I'm going to save. And how am I going to do it? How am I going to automate it? Well, I can open a file with number I unit. I unit, suppose, is defined to be 71, and uh, open a file with a certain file name and file name 1, where the values of file name and file name 1 keep on changing as shown in this line. So initialize underscore, and it will be concatenated with the value of CI. CI's value is going to keep on changing. Here it is 0, but later it is going to be 1000, 2000, 3000, and so on and so forth. And here, basically, one is going to concatenate initialize b underscore, again the value of ci at the currently it is 0, and at the end dot dat. Okay, so just to show you, because I had already created it and I had been playing with it. So initialize underscore, suppose 10,000 is the iteration number, dot dat. And similarly, initialize b, suppose initialize b underscore 14,000 iterations, dot dat, and so on so forth. Right. So that's how you do it. And well, I have written the code, and here you see that total number of snapshots might be 4000, but number of iterations is varying 1 2 3 4. And when mod knitter comma and snapshot, that is every 1000 iterations equal to 0, then I am updating the value of file name and file name 1 as initialize I0. You're going to have knitter. The value of knitter is going to replace I0 here, the iteration number, and it's going to replace the iteration number. Knit is going to replace I0 here, initialize B, and I'm writing down, here again. So I'm opening a file, somewhere I'm opening a file, iunit and iunit B, where these two are defined here. And in these two files, I'm writing down the lattice size iijj. I varies from 1 to lx, jj varies from 1 to ly, and I'm writing down the values of temp a and temp b, the new values of these variables a and b at so I'm going to write that down, right? So moreover, once this is written down, right, so maybe, yeah, I'll just clean up, I think, but clean up this a bit. Now you see that it is we are running our code for this set of parameters, right? And it has the entire Fithugh Nagumo implemented. So this is basically I'm saving the code. I am compiling the file, running the file. So it's going to run for 1000 to 2000 iterations, right? And what is going to happen is so it has created 1000, then 2000, 3000. It has basically computed, initialize for different values, initialize B for different values. What's inside there? Just let's have a look. The different lattice sites and the value of A is saved here in the third column, and it has 3600 lines for a 60 cross 60 lattice. And similarly, these are values of B, and they had been initialized randomly, if you remember, and 3600 lines. And how do you plot it? For that, there is a domains.m file and a domains b.m file, where I have specified the lattice size to be 6060. Then different variables like load, initialize.dat, etc. Uh, Basically, what I'm doing is that's being so I'm automating that stuff, and 40 snapshots saved every 1000 iterations, right? I and this value n, it's being converted from integer to string, right? And once it has been converted to integer to string, I am string concatenating a, which is initialize, b, which is this, and c is dot dat. And I am automating the loading of these files. It's very similar to what was shown, I think, in Ising, right? So I'm automating this load dot d. What is d? It is this concatenated set of uh, initialize underscore number dot dat. It's loading the data, it's evaluating, it is here that it is being implemented. Furthermore, these are all MATLAB commands which I have automated, right? So a and b is again, a is this and b was this number, and so on and so forth. Now I've converted it into an appropriate uh, 60 cross 60 lattice, which is being converted here in this step. The third column is being read here. The third column is being read here, and I'm converting this entire lattice into so sorry, I'm converting the third column into a 60 cross 60 lattice in this step. Please read up if you are interested. And then using p color, I am doing a color map. I am defining the range of the color map to be minus zero point 0.5 to plus zero point 0.5, and basically so that I can visualize it. Every snapshot, and 40 snapshots are going to be printed. There's going to be a gap of zero point 0.1 seconds. I can of course increase this pause to 1 second also, and I'm at the end. I'm also introducing a color bar, right? So without much ado, just let's look how this looks. So that's the domains, and similarly, I have domains B, right? So you see that at different points, A has somewhere higher densities and somewhere lower densities. Now it's interesting because diffusion equation tries to homogenize the densities, and moreover, when we switched off the diffusion equation and we were discussing only the Fithugh Nagumo terms, we saw that basically it again reaches a stable point. Every point, if it's starting between 0 and 1, it reaches a stable point close to 1. I mean, if there was no alpha, then it would reach exactly equal to 1. Um, and so on and so forth, right? But here we see the emergence of patterns. Of course, we don't have an intuitive understanding for it, but the aim of this was to basically produce Turing patterns. Of course, we're going to discuss and analyze it. And this is this blue to yellow color range. So you see that somewhere you have high densities of whatever this yeah, zero point 0.5 or even higher, maybe there's a cutoff here, and somewhere you have this blue. Now, just to start playing around, what one can do is also have a different range uh, for a color map, because this range of colors I figured out is not so great as discussed with somebody in class. So the color map, I'm changing the range of colors to cube helix, and let's see if we also change the pause to say 0.3 seconds. So you'll see the entire movie will run a bit slow, and just let's try what happens. Okay, so this is sorry. So I think the color has already. Uh-huh. Okay. So I hope I have saved this with the color map, and let me run this. I don't know whether you're noticing, but it's running a bit slower than previously. But it's changing, it's plotting every snapshot every 0.3 seconds, and this is the range from white to black and blue and green and yellow. So I'd prefer this color range. Okay, and okay, we can also plot domains B. Let's see what happens. Okay, here I haven't changed the color index, and it somehow follows it, but it's more diffuse. That's what you will finally see. So we have managed to produce all these patterns, and as we change these numbers, they will show various patterns as long as we set the criteria, but we still don't have an exact understanding of what is happening, right? So how do we go about trying to do that, at least partially? Because let me tell you that I mean, Fithugh Nagumo has been around for 40, 50 years, and there are still papers and theses being written, as I figured out. So I think it has a very rich history. But anyway, so this, if you want to understand it better, I'll just have a different recording. At least here we have produced it. Now you can play around on your own. uh, While if you want to develop an understanding, there will be another recording of this. Okay, so this is domains B. Just let me stop sharing my screen and stop sharing, and moreover, I'm going to stop recording as well.